страшного.
Very good.
No, so in previous class we have started the full dimension theorem. Group principal ideal theorem. And so it says that first of all, so the variant. Yeah. So let me mention only the generalization of it. So suppose ideal I is generated by the collection of elements. Then any prime p, so any minimal prime containing I, any minimal prime p containing I. So codimension of pi is less or equal than R. So that means that each equation gives you, it decreases codimension by 1. And codimension is the length, so it is, codimension is the dimension of the quotient. So of A modular P. Yeah, so this is, it has only one component, and so you are taking the length of the sequence between P and P. Yeah, so if so one can state the converse of this statement. Yes, so suppose yeah, but the converse is not exactly like this. I mean, so suppose you start with so converse. Yeah, so this theorem says that every, so whenever you add the component, so whenever you add the equation, the dimension drops by 1. Yes, so namely. But here we do not have well-known, I mean, here instead of dimension, we precisely use the notion codimension that in commutative algebra behaves better. And here there is the following proposition. Suppose you have P is a prime ideal. P is a prime ideal of codimension. Prime ideal of codimension equal to R. So then I claim then there exists a system of parameters, so the collection of elements, such that P is a minimal ideal, such that P is a minimal ideal over I equal to this set of the ideal generated by this elements here, so x1, etc. xi. Yeah, so what does it mean for us also geometrical? I mean, this has the following interpretation. So first of all, note so remark. So as we have learned, yes, so that minimal ideals containing I are exactly minimal associated ideals. So minimal ideals by containing I. So that they are in bijection. Minimal elements of the set. The set of associated prime ideals, A moduli. This was discussed in previous class. And also we know that since P is minimal, yes, so after factorizing by I, it became, and after factorizing, you see that this it is so if you take A mod pi, so this is if pi is minimal, then A mod pi is Artinian locally. So if I is minimal over I, and and the A is local. So let us also so I would state like this. So then localization of IP module IP is Artinian local. Artinian local. So, the corollary of this proposition, then, if you do look at this statement, that x1 xl R plays the following role. It is called the system of parameters. So let us call the following definition. So x1 xr is called inside P is called system of parameters. If A mod if pi is minimal over is a minimal over x1 xr or just equivalently A mod if you localize and factorize by x1 xr, it is Artinian local ring. So in a sense, well, what are Artinian local rings geometrically? These are some kind of geometric interpretation. This is some kind of, if you already have a Artinian local ring, it plays the role of a point and a sufficiently small neighborhood. So a point with a small neighborhood. So first of all, because the object, so we're speaking about the point, because the object is zero-dimensional. If you want to get the intuition about the small neighborhood, then it, I mean, if you have just, yeah, so because you have the full 14 in ring, you have the full filtration, and at some, so if it is local, then at some point, well, in case if it is opinion and consists of even of several points, at some point you will have some power of maximum ideal here that it is equal to 0. Yeah. So in a sense, it looks like you have so here you have a modular m. So this is a field, and a field is just a function of the point. Yes, if you are thinking about functions with the values in the field itself is associated with the functions on the points, and further terms. Yes, so like in order to get a from just a mod m, you should go further down to the ideal of the form m mod mn, and this is filtrated by finite dimensional vector spaces, and in a sense it looks like, I mean, if in the easiest situation it is just the tangent space, in the more complicated situation one should say that it is a jet of function, because in a sense if you apply, so why it is a jet, why it is called a jet, because you are thinking about taking the polynomial ring, yeah, and then maximal ideal is just the natural homogeneous maximal ideal here, and you are just saying that these powers of m, so if you look at, for example, m I modular mi plus 1, so what it is? What is this one? If we are speaking about term of I, we are allowed to multiply I terms, yeah, and plus something. But if taking modular mi plus 1, meaning that you are, if you can multiply by something else, it becomes 0 in the quotient. So what it is? So for example,
Однородные полиномы там какие-то нет.
Да, однородные полиномы, а какой степени?
И ты видишь.
И ты, да. So these are just homogeneous polynomials, polynomials of degree less or equal than equal to I, and this is just because it is checked on monomials. Yes, so mi. So if the elements of mi looks like are generated by monomials, yes, so m is generated by these functions, mi are generated by monomials, but also you are allowed by multiply by the element of k, yes, so of the whole whole polynomials, but this is killed when you, I mean, if this polynomial has no, if it has constant term, then you can extract precisely the monomial. If it has non-constant term, so this non-constant, you take it, and the multiplication by non-constant term falls into m plus mi plus 1. So if you are thinking about m modulo m square here, in this case, it is just it is just the collection of x1, xn, yeah, so that the vector space generated by this variables, and this is nothing as cotangent vector space. Yeah? So I mean, it is not one can think. So that means that the information that is contained, for example, in so if I put it in a modular m square are the following. So this is a value of polynomial, and the next term is a linear term of this polynomial, and this is collection of coordinates. This can be associated with. It is not vector; it is co-vector. This function. So if you think of this set as the functions on a affine space, yeah, so that the coordinates are just functions on the vectors, and this is the dual object, the tangent space in the plot. And this some kind of motivation should be kept, so that we shall return to this a little bit further. So in a second. So then you I think, and Artinian local ring, it looks like a neighborhood. So the introducing, I mean, it is a point with a neighborhood. So this kind of thing is the following. So you had the ideal, so P is a prime ideal, and you are approximating this prime ideal by the sequence of parameters. So this means that this set is so the inclusion of this set geometrically, what does it mean? Yeah, so that means that you have a rather complicated variety, and you start cutting out it by the equations. Yeah, so that the collection of equations. This is here, but then this when we are able to construct such sequence, I mean, it's not clear that we are able to do it, but we shall prove it in the proposition. And this means that more or less this thing that we got, it is very, very it almost cuts P, yeah? So it is very near to P. Yeah? So it is as if, for example, you are cutting a zero not as x equal to 0, but for example x squared equal to 0. Yeah? So this is still a good system of equations at some sense, and it geometrically it cuts out the same variety, but not precisely this prime ideal. And it looks like saying that it is Artinian. It looks like it is. We have the following data. It is a point on this prime ideal plus some kind of additional information about infinitesimal neighborhood of this point. So yeah, so I was just yeah. So everybody when speaking about this kind of so this is called in a sense in algebraic geometry this object is called the nilpotent thickening, yeah, because this is Artinian local ring, and in maximal ideal, all elements become nilpotent, and this. So usually at some books, people are drawing this by vectors, and yeah. So I was also thinking about that, and then I at some talk. And I was somehow embarrassed about this kind of thing. And at some talk, I also had this was a talk of Manfred Lang, who was also some kind of so he said that at least this picture of drawing these vectors, it is in a sense bad because what the infinitesimal thickening, this element in the infinitesimal thickening element in M, this in maximal ideal, or in this prime ideal modular this collection of elements. Yeah, so this is not the vector, this is covector. So it one should so existence of nilpotent, it is a vector because it is covector because it somehow functions on the vectors.
Yes.
And it is bad to draw it by the vectors. However, I mean, if you are drawing covector, it is still a vector, but in the other space, not just. So it is somehow these pictures are confusing for beginners, but not for I would say for experts. And I mean because but in a sense, so you should understand that pictures of this form usually do not mean something very clever. So I mean. This is just to give you some kind of intuition, not the real picture. Yeah. So let us prove the proposition of existence such sequence. So yeah. So what we should be doing. So this is induction by. So we shall start drawing EI, so that we shall start constructing this ideal generated by this set of elements. So our aim is to start constructing this sequence, and we shall do the induction by codimension. So, for example, we shall do the following. So, by induction, we shall construct. So, we're constructing this sequence. With the following property. So this sequence of parameters. Yeah. So we shall also admit the following. So it will be not only the sequence of parameters. We have the plus, yeah, so we have proved on previous class, yes, that if you have this sequence, then all prime ideals have codimension less or equal than I. And we shall construct the sequence of parameters with more strict assumption. So we shall assume that all components, so any associated prime ideal, so minimal associated prime ideal has codimension I. So prime ideal containing I, this has a codimension exactly I. So it doesn't have larger codimension. Then, yeah, so then of course what can happen, so you are starting constructing, so what can also happen in this theorem, yeah, so you are constructing this system of parameters, but P is not, so P is not only minimal prime ideal, so it can have So the system of parameters that we're constructing, it has several components, so PIs, but it gives you some local information around P, but yeah, so it can also have several components part of the same codimension. So this we are not proving that this component is unique.
What is PI?
What?
What is PI?
PI?
Yeah.
Yeah, I mean this is just so you start with I, and you look at the set of associated prime ideals. So so our aim is construct I that consists of is generated by R elements where R is codimension, and you can look at the set of associated primes A modulo I. In the construction, P is minimal, so P is the element of this, but you can have other minimal ideals, the other minimal prime ideals that contain I.
Okay.
We do not guarantee that P is unique, yeah, in the proof, and this is somehow, I mean, because it is hard to control this, and when you are adding equations, so we do not have this information, and but what about other components? At least they are of the same dimension, so we can control the same codimension. Yeah. So suppose just yeah. So just. Yeah, so suppose already, so I shall put the index I, yes, so for x1, yes, so let me put j. So let me put j for, so yeah, so by the yeah, so suppose you are just so suppose we already constructed this sequence at some point I. We want to get a new element. So let us denote P J. So this. Да?
Он еще кондукции будет вам.
Но шаг индукции такой, что мы, то есть мы вот действуем по индукции и доказываем следующее предположение. То есть, как бы вот, давайте напишу вот такое предположение. Мы строим вот такие элементы, такие идеалы, да, добавляя последовательности элементы, чтобы все ассоциированные, которые, первое, что, конечно, и лежит в P, то есть это последовательность элементов из P, а второе, что все ассоциированные простые идеалы, они бы имели по разменности в точности их, то есть сколько у нас элементов. Это выбор, последовательный выбор элементов. Хорошо? То есть, нулевой шаг это выбор, в смысле вы стартуете, элементов нет, надо добавить элемент. Поэтому, как бы тут базы индукции как таковой нет. Да? То есть она бессмысленна. Вот мы сразу начинаем строить элементы из P. Хорошо? Вот, соответственно, мы so we start with the element and with J and consider the set of denoted by the collection PJ. So the minimal prime ideals containing containing J, and in this case, the codimension of Pi is just I. No? Pj is just I. No? So this is so I is fixed. Yeah. So and then we want to, of course, what we want. So in order to increase codimension, yes, so we have to take the element outside of the minimal ideals. Yes, so take x I plus 1. So this ideal will sorry, just in the codimension I realized I have written the wrong formula here. This is dimension also, but this is dimension of the law. So codimension is dimension of the law. I'm sorry for this misprint here. So if you are yeah, so this so we are talking about the and yeah, and here I was talking the length of chains that were dimension. Yeah, so that we should talk here about the chains between 0 and p. Yeah, so that 0. Yeah, so this is codimension. So
Который еще с этого идеала называется.
да. Ну, просто мне геометрически приятно говорить коразменность, да, потому что, ну, это реально коразменность многообразия, которое задается идеалом. Ну, то есть, so we take x I plus 1 in this in the ideal in the ideal P that we want to approximate. So that, and this we want to increase codimension, but this all chains stops at Pj, so we put so we put this x, so we take xi plus 1 that is not contained in any, so take xi plus 1 is not contained in any pg, and this is so this is a claim actually, it's not clear, so this is claim, so we can take this kind of element with this property, yes, of any j. And let us understand this point, and this is just prime avoidance theorem, so that we shall recall, just avoidance lemma. Yeah, so that says the following. So suppose you have I that is contained in the union of PGA, so I shall write down this in the strongest, well, not in at some form. So actually there is also the prime avoidance lemma for modules, but it is it looks like slightly different. So this so this are collection of prime ideals. These are any two ideals, and if this holds, then I is contained at some pj, or so I is contained in J, well, in some of this J1 or J2. So this, yeah, but here we shall use it only for prime ideals. So just yeah. So suppose yeah. So how this is constructed? So at a point, so the proof gives you. So proof gives the element, gives an element of I such that x inside I such that x doesn't belong to all pg and all this x doesn't belong to these ideals G. X doesn't belong to J1 and J2. So, this economy is, I would say, time consuming for readers, so I won't use it. So, this. This and you can apply this simply to the collection of ideals. So you see that so P is not contained in any PG. Yeah, so P can be not equal to any PG. Why? It is very yeah. So the sorry. So here I would say just I wanted to say that I wanted to say the following. So in the proof you do the following. So if you assume the converse is P is not contained in if I is not contained if I is not contained in any of P, J, and I is not contained in any J1, J2, we construct an element X inside I, so such that.
А можно спросить,
Да.
G1 и G2 это что у нас?
Просто два еще дополнительных идеала. Это, ну, просто обобщение. Ну, Батье Макдональд дилемма об обхождении написано для объединения, ну, для простых идеалов.
Ну, G1 и G2 ставится так же, как и G, да?
Что?
G1 и G2 ставится так же, как и G. Ну, вот у нас был там предыдущий G какой-то, или просто какие-то...
Нет, G1, G2 это просто, ну, как бы еще, ну, просто время обхождения у вас есть объединение простых и еще два каких-то идеала. То есть вы говорите, что если идеал лежит в объединении каких-то простых
Ну, то есть
еще...
они с G никак не связаны?
Никак не связано. Да, это просто, ну, букв мало. Да? То есть идеалы обычными буквами I или G обозначаются. Вот это просто какие-то. То есть мы находим, so we construct X such that X doesn't belong to any PG and for any G and X doesn't belong to J1 and X doesn't belong to J2. So this is the way to construct.
But I is inside union of PJ and J1 and J2, right?
Yes.
Yes, but
I mean, if I mean, this is negative statement for this one. This is negation. I mean, suppose I is contained in this union.
Yes.
So we want to derive that I is contained in sum of Pj or sum of
J1, J2.
or J1, J2. Yeah. So the converse for this statement is the following. Assume this doesn't hold, then we shall see that I is not in the union of these ideals. But I is not in the union of these ideals means that that you can find the element that is not in
Inside
any.
Yes. Oh, okay. So we
yes.
need to show this the existence of X.
Yes.
Okay.
So I mean, in the proof of in the proof of prime avoidance, so we have discussed this. But I want to recall this part of the beginning of the statement because we are using it not the formulation of prime avoidance but existence of this element. So if P is, so notice that P is not contained in any Pj, and the reason for this is very simple, it is inductive. Yeah, so, and this is precisely explains why we have to assume this additional assumption on codimension. So notice that we have this assumption of codimension, and that all associated prime components has codimension exactly I, and codimension of P is I plus is bigger than I. So that means pi is not one of them. Yeah, so pi is not contained in any Pj since codimension of pi is bigger, is strictly bigger than I. Is strictly bigger than I. Yeah, so otherwise. Yeah, so you see that if you have P was contained in Pj, so the sequences inside P gives you the sequences in Pj. Then codimension of P is less or equal than codimension of Pj, and but by assumption, inductive assumption, codimension of Pj was equal to I. So that they are not equal, and P is not contained in Pj. So this implies that P is not. This implies that we can apply prime avoidance. Prime avoidance. And get element that is inside P, but x I plus 1, that is inside P, but x I plus 1 is not inside Pj for any Pj. And now it is almost, so it is almost everything. Yeah, so we have to prove that now we have to take, we have constructed, J, so this EI plus 1, so we have added the element, and we have taken, so put Pj tilde, so put Pj tilde to be minimal prime ideals lying over so containing, better to say containing. Containing. Here I plus 1. And we have to prove that codimension, the codimension, so we have to prove that codimension of P, J, is precisely is equal to I plus 1. So previous theorem tells us that so we have codimension yes, yes, so we have to we already have this kind of codimension. It is less or equal than I plus 1. Yes, so this is because we have the sequence, so by previous theorem. So this is cruel principal ideal theorem actually with this additional technical proof, so by previous statement. And yeah, so generalization of cruel principal ideal. And this this codimension is less or equal than I plus 1, so we have to prove that codimension is actually larger. Yes, so we have to prove that PJ is so codimension of PJ is bigger than equal to I plus 1. But notice that note that PJ tilde, so it contains I, yes, so from the beginning. So this implies that that PJ tilde contains minimal prime ideals lying over I. So precisely P1, etc. K. So these are prime ideals. And by existence by xi plus 1 that is lying in PG, so and xi plus 1 that is not inside this other other PL. So by the choice of xi plus 1, so this implies that Pj tilde is not equal to this minimal ideals, and this of course implies that codimension is larger. Yes, so P tilde contain them, so this implies that codimension is larger. So codimension of Pj is larger than codimension of PL, and this is precisely this is precisely the statement. Yes, so we have we will see the opposite equality. this gives you this term. So this this motivates choosing the system of parameters, and now I want to pass to some kind of also discuss some notions that is related. So. Yeah, so let us let us sum up what we have said. So suppose A is a Noetherian local ring. So then we call x1, xn is called the system of parameters. So if first, so A modular x1, xn is zero-dimensional ring, zero-dimensional, so Artinian. So this is equivalent to saying that the M modular x1, xn is nilpotent. And since we are working on the Noetherian ring, being nilpotent is equivalent to consist of nilpotent elements. The third is that x1, xn is primary ideal associated, is primary ideal associated with x, so with M. And the fourth is just saying that where the system of parameters lives, and so one can put the power of maximal ideal inside this ideal, and this so you can put inside them for some M. And so this is just summing up what more or less what we have said, and this suggests the following, that the ring is called regular. It's called regular. If dimension of this ring is equal to, so this is so dimension, crude dimension, that this is a length of the sequence of prime ideals, is equal to dimension of M miniature. Я завис просто. So dimension of M modular M square over K, where key is just the quotient of A modulo M. Yes, so notice that M modulo M square is a modulo over A modulo M, so this we can take this dimension, and this is actually the following, so that yes, so we shall also see. So in general, so remark. In general, we have the following, so dimension of M modulo M square over K is bigger or equal than dimension of A. And this is just what it is. So as we have discussed that M modulo M square, it is somehow it is a tangent space. Yeah, so it is, well, this is cotangent space. This is called cotangent space. So it is a dual to that tangent space. And it is, so if you try to calculate it, you see that it is, so in algebraic geometry, it is just the set of tangent lines to the point. Yeah, so it is clear what does it mean. So in algebraic geometry, it is more or less clear what is tangent line. Since you can do the following, so you can, if you want to intersect, tangent line, let me make some kind of remark about that. Yeah, so here we so if you are talking about our variety, so in a variety X somewhere, and you have a point P. Yeah, so you are talking about I. This is ideal that defines X, and so I is generated by the collection of equations, and if you have line L, you have a natural restriction, so L isomorphic to A1, so you have so each Fi it restricts to this line, and to get so we get a polynomial in one variable, so polynomial in one variable, and you may speak about multiplicity of roots. Yeah, so that if you already have the line passing to the point, so if you have the property that here belongs to this line, so this equation looks like x times, so, and if it is 0 coordinate on the line, here corresponds to 0 coordinate on this line. So this is just x times gi, where gi is some polynomial. So you may think of the following and ask if you have, so line is tangent, L is tangent. If you take this ideal, restricted to the line, and it contains the ideal generated by x squared. Yes, so that will give you the tangency. And if you are thinking about this set of lines, one can associate it with the dual space to this line with m modulo m square, simply because somehow the ideal m square measure if x belongs to this ideal, or x square belongs to.
Под L мы понимаем что-то, что задается...
L это просто геометрически прямая.
Там буквально прямая.
Ну, прям буквально. Ну, в смысле, вот в этой. Ну, в смысле, что вот это все лежит в афинном пространстве над полем. Поэтому, ну, как бы, это вот вопросы... Ну, то есть мы смотрим на алгебраическую геометрию, пытаемся проинтерпретировать то, что нам понятно с точки зрения алгебраической геометрии в терминах коммутативной алгебры. Да? Когда это нам удается, мы можем после этого забыть про алгебраическую геометрию. Ну, это шутка, конечно, но мы можем просто использовать те понятия и назвать это по касательным пространствам. Хорошо. И использовать это таким образом. То есть, so now I want to prove the goal is following. So suppose A is Artinian local ring. Suppose that for M is a regular local ring. So I want to prove that it doesn't have zero divisors. So the proof will be like this. So as a byproduct of the proof, we also will see that this inequality for general rings. So that's let me just regular local ring has no zero divisors. Surprisingly, regular local rings they behave. They have much better behavior. First of all, if there is an operation of completion. So if you this will be not proved. So remark that operation of notice that we have proved that intersection of mi is equal to 0. Yeah? So you may take the following. So you may take a limit of A modulo mi, meaning that you have the following. So you have a sequence A mod m. Yeah, so you have A mod m square, A mod m cube, and you can consider the limit, which is collection of elements such that they map to each other. Yeah, so let me denote it by P1, P2, P3, etc. And you have an element A1, A2, A3 here, etc. So of course you may consider the sequences that are consistent with each other, and the condition of consistency is the following. So AI is equal to P I minus 1 from AI is equal to AI minus 1. So this is consistency condition. And one can see that this object form, so after you take this set of sequences, this set form the ring, yeah, so you can multiply this collection of elements. And this is called this kind of limit. And so collection of such sequences. And notice that you have also the map from A into all the of the elements of the system. Yeah? So this just A maps to this kind of thing, and of course the kernel is just the intersection of this. So phi is the natural map, and kernel of phi is just the intersection of all mi, and this is equal to 0 in this case. Notice that this construction can be written in a categorical way, yeah, so that first of all, in order to do it, you have to mimic simply this kind of thing, so that you are just having the collection of A1, A2, etc., AN, yeah, so that maps into each other. And then you are speaking about the...
У нас видео
Что?
У нас видео нулевой фильм.
Чего?
У нас нулевой ядро фильм.
Ну потому что ядро что такое? Ну это те последовательности, ну вы берете элемент из А, отправляете его во все элементы здесь. Ну, ноль это нулевая последовательность. Но нулевая последовательность это говорит о том, что все омытые, ну, они принадлежат всем омытым, а вот это равно нулю по лемме Накаяма, если вы помните, что если вы вот эту штуку умножите на омытое, то это останется тем же модулем, просто потому что у вас сдвинутся элементы пересечения, и как бы вы просто первый элемент выкинете, он все равно несущественный для взятия пересечения, и тогда вы по лемме Накаяма увидите, что у вас ну вот m на ядро φ равно ядру φ, отсюда следует, если ядро конечно порожденное, а это так, поскольку мы работаем в неутровых кольцах, то тогда оно нулевое. Хорошо? Вот. So the theorem that if you have K is a field and A is a regular local ring, over K, and you see that also. So you have additional condition that A mod M is equal to K. Of course, yeah. So this is true. I mean, it could happen that K maps here, yeah, but we also assume these two conditions. Yeah, so this is called A with hat. So this construction is called the A with hat. So then A with hat is equal to the ring of formal power series. So this is a very famous theorem, and it says actually that local rings in a small neighborhood, it behaves uniformly. They are the same object, more or less. And however, there are still some assumptions. And also, regular local rings are factorial. So that, this is a more complicated theorem, so we can, so this is theorem that A is a regular local ring. Then it is factorial, meaning unique factorization domain. So maybe it is logical a good time to make a break. So after that we shall discuss that. The ring has no zero devices. So let us have 10 minutes break.
Можно вопрос?
Да.
Я вам писал первую домашку.
Да.
Вы ее так и не посмотрели?
Ну, пока нет.
То есть это нормально?
Это нормально.
Я просто думал, мало ли там.
Нет, это нормально. Я, как бы, я потом буду делать курсы. Потому что мне очень неудобно 2 раза все смотреть, потому что...
Я понял. Нет, я
Просто
просто увидел, что вы прочитали,
Да.
может, что-то туда я отправил.
Нет, все хорошо. Я просто, это дедлайн был скорее для вас, чтобы вы занялись этими задачами раньше, да, а не в последний момент.
Suddenly I found this site. Is this solution homework to solve and solve?
Yes, also. Yeah.
Okay, then can I take some days to solve and send to you because I didn't.
Yeah. Okay.
Okay. And also, like, what is the last date of submitting the term paper?
What?
The term paper.
Can you repeat? I
What
didn't
is the,
heard.
what is the last date of submitting term paper?
Submitting the solutions.
No, term paper means the research work of first year master's degree.
This, I don't know, you should consult the teaching office or, there is the special site, I have put it actually. The site with holidays and deadlines.
Okay.
Yeah, I have put, in the Telegram, I have put the link after you told me about
Yes.
the official holiday, yes,
Okay.
that I found it, and
Да, мне сейчас нужно перейти, я хотел узнать сейчас, экзамен он будет полностью задачи.
да, я
То есть
просто,
вы просто напишите задачи, их нужно написать. А какие-то числа примерно будут?
если хотите, уже можно.
Хорошо, то есть можно вам написать, просто и будет числа задачи.
Я просто в чат тоже.
Да, хорошо. И потом в течение июля вы будете проверять, на
Да.
концу июня надо будет написать.
Да.
Если все онлайн, я могу и не назваться в искать. Да, хорошо. И тогда еще вопрос. Вы накладывали первый листок, его написал, а там еще был такой кусочек второго
Я
листка.
думал его расширить, я знаю, расширить.
То есть это добавить
Да.
задачи. Окей, хорошо.
Это будет экзамен.
Да, спасибо.
Вы уже уезжаете, да?
Ну, я хотел в конце мая уехать. То есть у меня вот 25 числа очный экзамен последний. И
Хорошо.
вот. Ну, как бы здесь же лекций не будет никаких в июне, как я понимаю.
Ну, я хотел еще 1 июня сделать, но как раз посмотреть.
Ну да, вот, ну то есть, а в основном как бы у меня
Не 1, 3.
Да, вот. Гомологическая алгебра у меня там закончилась вообще в середине мая. Там какие-то в МИАН курсы тоже закончились или заканчиваются.
Хорошо.
Там семинар по арифметической геометрии, на который я хожу, он тоже до начала июня. Там.
До свидания.
Счастливо.
еще вопрос. Я общественной магистратуры, и да, нам нужно, во-первых, говорили, на первом курсе сделать какой-то доклад.
Да, ну вы где-нибудь на каких-то научных семинарах делали?
А у нас просто на научном семинаре он теория представления, но там больше физики. И я физики как-то не очень.
То есть вообще совсем никаких докладов не делали, да?
Нет, получается, первый семестр не делал,
А вот,
а во втором у меня просто научный семинар накладывается с алгеброй МИДи.
Ага, я его просто только в записи могу
А,
смотреть.
я не успеваю.
Работы вы какие-нибудь
Я
сами?
сейчас курсовая по базе фан-центра, СН и как сказать,
Ну, перспективно. У вас там семинар.
я закончил, там
У вас кто? У вас
там почти все уже закончил, там после
Ну, хорошо, да.
Да, ну давайте продолжим. Yeah, so but this theorem about about factoriality is quite complicated, and so we shall discuss that just the following that theorem that AM has M is a regular local ring. So then A has no zero divisors. Has no zero divisors. Which is completely so even this is not evident. So proof that so idea of the proof is the following. So just we have to after taking M mod M, so we have to choose. So we have condition that dimension regularity is the condition that dimension of A is equal to dimension of M modular n square over K. So this tells you that this we shall prove the existence of the element in maximal ideal such that you can pass to a modular this maximal ideal and modular principal ideal, and this will be also a local ring, but I claim that this choice can be made in a way that so this ring remain regular. This will remain regular, and this will allow to proceed by induction. Yeah? So let me. So the idea is that if that Yeah, and geometrically, if you think about what is x, it is just the element, it is one equation, and this is, so we just take the variety and cut it to pass to hypersurface, and then to smaller varieties of smaller dimension. And the claim is that during this process, we can make this process in a way that the ring will still be regular after this process. So first of all, we have to do it. So what is base of induction? Yeah, so base of induction. And induction is on a dimension of A. Yeah, so that induction on dimension of A. So here, base of induction will be completely non-trivial. So in this part of commutative algebra, when we are speaking about system of parameters, one should notice that the base of induction is, usually base of induction is trivial in most branches of mathematics, but here it is not. And it will refer some some objects like associate prime decomposition, and this is actually natural. It is so you cannot avoid it. You cannot simplify this. So. This base of induction is that dimension of A is equal to 0. So this implies that A is Artinian. So this means that just simply dimension of, so here clearly M modulo M squared is finite dimensional vector space. And notice that here you have M. So clearly this is larger than 0. Yes, so the ring is it is very rare than the ring is regular in this case. So this implies that M modulo M square. This is vector space, so this implies that saying that dimension is 0, it is simply the space is equal to 0. So that M is equal to M square, and we can apply Nakayama lemma. So by Nakayama lemma, simply maximal ideal is trivial. And this implies that A is a field. So this implies that A is a field. So it has no, so it is domain. So no zero devices. So and then you just the second step is the following. So suppose A is not domain. So this means that the set of zero divisors is not trivial. So you have the set of zero divisors, and each zero divisor is what? So if you have an element and a non-trivial annihilator, so if you have x zero divisor, let us recall that. This means that annihilator of x is non-trivial. And this means that the maximal annihilator, so there exists y that is maximal in the sequence of annihilators that are containing x. So you are just multiplying x by some elements that are not in the annihilator, and you can just you see that you can enlarge. So y is equal to x times z. Yeah, so that annihilator of y is associated prime ideal. So this is maximal, this is prime ideal. And this is associate prime. So the any element can be put inside the any we look at the set. Sorry, I wanted to say that not x. You start with some element. So W is a zero divisor. Then there exists x such that W belongs to this annihilator. Yeah, so this means that W is precisely is in some prime ideal, where prime ideal belongs to the set of associated divisors, associated prime divisors. So now you see that this set of zero divisors, yes, so it is contained in the union where P runs through the set of associated prime divisors of A. And notice that any such P is, of course, it is a zero divisor because it is annihilator of some element. So you get the following. So note that m is not equal to 0. M is not equal to m squared. So otherwise, dimension of A will be 0. And we assume that the dimension is larger. Then you can apply prime avoidance, but apply prime avoidance to the following. So to I equal to m, and the collection of ideals, so the union of P where P runs through the set of associated prime divisors, and the union of m squared. So we have to find an element, yes, or a priori, yes, so to reduce the dimension of m modulo m squared, we have to find the element in M that is not in M squared. So this means that we shall get an element x inside Yeah, so notice that M, yeah, so note that, yeah, so why prime avoidance is applicable, so note that the M is not equal. So M is of course not contained in M square, and M, if M is contained in P for yeah, so notice that P are just M, so M will be contained in P, so for some P is not possible, so this will imply that M is equal to P, and just yeah, so here I'm taking not all the set of. So here there is important issue in the condition that we want to apply. So I also assume here that P is minimal. So I take not all prime divisors here, but only minimal ones. Okay. So then if M and P is minimal in the set of associated prime divisors, then this will imply that M is equal to P, and P is minimal. So this since P is minimal in associated prime divisors, so P is minimal prime containing 0. Sorry. So here we have the situation is more simple. Here we had a local ring, yeah. So that, yeah, and here we also P is minimal. No, it's not simpler. So P is just minimal prime ideal containing 0. So this means that just M is minimal over 0, so this means that and in the same time all ideals are contained in all prime ideals are contained in M. Yeah, because M is maximal, so all ideals are contained in M. So this and P was minimal, so between 0 and M, and P there are no ideals, so no ideals. And this means that M is only prime ideal. And this implies that ring is Artinian. So, which is contradiction? So, we are able to apply prime avoidance. So, since we are able to apply prime avoidance, so by prime avoidance, so this means that there exists element x in maximal ideal such that X is not inside P for any P minimal in the set of associated prime ideals, and also X is not inside M squared. This is actually explanation, so the way we apply this prime avoidance theorem. This is explanation why we use this strange formulation of prime avoidance with two additional ideals. I mean, I haven't seen, I do not remember if I saw this theorem applied to more than one not prime ideal. Yeah, but at least you should have a lemma where one ideal is not prime, and this means that so we can choose this special thing, and notice that since all ideals that they belong to this all zero divisors, they should belong to this minimal prime ideals, so that means that this means that this implies that X is not zero divisor. And then you can yeah, so you also will have to calculate the dimension. Yes, so let us look at, so now let us calculate dimension of A tilde. Yeah, so we put A tilde to be A modular X. And so the question is how we can calculate a dimension of A tilde, crude dimension of A tilde. Then you take this projection, and if you are interested about dimension, then you want to speak about length of the chain. X in P1, etc. So if you are thinking about now so we were speaking about the codimension. Now we are speaking about dimension. So we are speaking about the length of such chains. But notice that so we want to understand how they are just related with chains in A. But notice that all chains of prime ideals in A, they start with So start with P0, where P0 is the minimal prime ideal, where P0 belongs to the set of associated prime ideals. Yeah, by the way, so here we also used an important fact. In prime avoidance, we need to understand that the set of ideals there is finite. So we used the fact that the set of associated prime ideals is finite. Yeah, so all chains of prime ideals, they start with P0, where P0 is the set, so this is minimal ideal, so P0 is the minimal prime ideal length, prime ideal that contains 0. This means that P0 belongs to the set of associated primes and minimal there, and this implies that X doesn't contain, is not contained in P0 for any such P0. So this implies that the chains starting, so at least, so chains starting at X, so they cannot start with P0. With P0. So this implies that dimension of A mod X0 is decreased. And now let us notice that. So we have proved the following. So this dimension, after this operation, we have proved that the dimension of A is decreased at most by 1. Yes, so that dimension of A tilde is less or equal than dimension of A minus 1. And let us look what happens with M modulo M square. So since X belongs to M and the X doesn't belong to M square, this implies that if you put M to be M modulo X, so that dimension of N modulo N square is equal to dimension of M modulo N square. Yeah, so you can M plus X modulo M square plus X. Yeah, so it is just this is second theorem on the homomorphism, and this is just equal to E of M modulo M square, where P is percent that map modulo X square, and this is just one element. Yeah, so just notice that this is a vector space. So and over K, yeah? A mod M. And this is one-dimensional vector space generated by one element. So this is P applied to ideal generated by X. One-dimensional vector space generated by X. So this means that this dimension is equal to dimension of m modulo m square minus 1. Sorry, here was without. So this so notice that. So what do we have? So if you compare these two things, yes. So here you have dimension of A is decreased at least by 1, and the dimension of n modulo m square is decreased precisely by 1. Yeah?
Я хотел сказать, что связь.
Что говорите?
Я хотел сказать, что связь тоже связь.
Спасибо. Yeah, so upstairs you have so you have the equality, and upstairs it has a smaller dimension. So this so if you so at least so you see by induction, yes. So сейчас, секунду, с неравенством соображу. And what about so this is by induction, and now we have applied. So in order to see about the dimension, so what about yeah. So what about minimal? Yes, so not that by Krull theorem. Yes, so this just I was thinking because it was not trivial theorem. So note that by note that if you have ideal, if P1 is minimal ideal, is minimal ideal containing X, containing X, then it means that by Krull theorem, so by Krull theorem, P1 is of codimension 1. P1 is of codimension 1. Yeah, so this means that the chain the chain that we are considering, yeah, so it looks like this, that you have P1, P2, etc. And if you look at minimal ideal that is contained in P1, so minimal ideal here, so X doesn't belong to this P0, so the length of chain is precisely actually dimension of A minus 1. Yes, so length of chain here. Starting at X is equal to the length of chain minus 1. So dimension of A tilde is precisely dimension of A tilde is precisely dimension of A minus 1, and this implies that by induction on dimension of A on dimension of A tilde. We have the dimension of A tilde is less or equal than dimension of n modulo n square, and this implies that so this is equal to dimension of A minus 1, and this is equal to dimension of m modulo m square minus 1. So this implies that dimension of A is less or equal than dimension of m modulo m square. So you see, at least we have proved that the inequality. And also we have to prove that you have proved inequality. So this means we have proved inequality. This means actually that regular local rings are in some sense external with this property where the inequality is just becomes equality. And then you have to prove that so by induction A mod X is has no zero divisors, since this ring is regular, so since in particular, so if when A is regular, this implies that A tilde is regular. But by this construction, so if you have a quality here, then you have quality when you subtract one. So if since Ax is regular, and if just so this implies that X is a prime ideal. But since X is not, so since X is not in any minimal, for any minimal prime ideal like over 0, containing 0. Since A of X is the main, so that X is itself prime ideal. But X doesn't belong to any minimal prime ideal. So this means that X is not minimal. So this implies that X is not minimal. Then you can find some minimal prime ideal. So take minimal prime ideal. But you can do the following. So now let us just study if this could be true. So now this implies that just any y inside Q so can be written since Q is a subset of principal ideal. So you can divide by X for some E. But X itself is not in Q, and since Q is prime, this implies that A belongs to Q. Yeah? Then you have this implies that any element of Q can be written as X times A. So where A belongs to Q. So this implies that Q is equal to X times Q. So since you have written a Y as AX, where this is an element of Q, any element of Q, and we have proved that this A belongs to Q. So, but X was in M, so we have X was 0 divisor, and sorry, X was not invertible. It was from the beginning was taken from M, And this implies that by Nakayama lemma, that just q is equal to 0, and this implies that 0 is prime ideal, because we assumed that q was minimal prime. And this implies that A is domain. So that is the proof. So now I want I think just I want to speak about a little bit about dimension theory, and what was today about this regular local ring was some motivation for dimension theory, and then I want to pass to the so-called Serre normality criterion. That is a little bit technical, so I want to just give you some kind of so to entertain you, I want to give you some just to go around, yes, some different topics. Okay. So Hilbert polynomial and dimension theory. And dimension theory. So the idea is the following. So let me say something about motivation. So motivation is how we can track the dimension from the properties of the ring. So suppose you have a polynomial ring. So here in the polynomial ring you have maximal ideal, and you want to, so now consider the following object. So consider, so notice that you can, yeah, so yeah, I want to start from one. Yeah, so we have noticed that mi modulo mi plus 1 are, so these are finite dimensional spaces. These are the set of monomials of degree I. Yes, we'll set just the vector space generated by vector space generated by monomials of degree I, exactly I. And then you having this vector space, you can calculate the number of such monomials. So what number of monomials of degree d in n variables. Who knows how to calculate it? Но это
Это количество Zhgun, что-то такое?
но тут как бы очень просто можно
Ну, у нас ничего.
посчитать, можно, ну как бы вот у нас есть d чисел, да, ну вот d элементов, которые надо распределить
Нам нужны
между...
перегородки просто.
Да,
такой,
да, это
перегородки.
как у нас любят говорить палочки и яблочки, да? То есть, типа нужно поставить this the elements and in between so to form the monomial x1 i1 etc xn in you have to put you have the elements and in between you have to put this on a place I1, this position on a place I2, etc. I3. So you have to choose how many positions?
Через d минус 1.
N minus one.
N минус 1, да.
So you have to choose n minus 1 positions.
Я уже привык, что это степень одной размерности.
N minus 1 positions. And the number of elements here, since position increases the number of elements, d plus n minus 1 elements. Places, yeah? And this implies that this is just binomial coefficient. And it is important to understand, suppose you you want to get, so you have a collection of numbers, yeah? Suppose you want to recover n, this n, how we can recover it? Yeah, so here it is, in order to derive asymptotics, it is better to write it down like this. Yes, so I mean it in order that the polynomial it looks like, so here just to get rid of n in the denominator, so like this, yeah. And of course this is what is asymptotics?
Мне кажется,
Но нужно поделить, да, ну дайте d факториал, n минус 1 факториал, по идее, да? И тут нужно написать, ну, от n плюс d минус 1, ну, тут тоже надо написать факториал, но вот как бы вот эти факториалы надо подсократить, то есть тут надо написать стандартную, ну вот, один из вариантов биномиальной формулы, ну вот, чтобы тут что стояло? n минус 1 элемент, да? Правильно? О, извините, не n минус 1, а тут стоит, получается, d элементов, да? d элементов. Ну, нам нужно поделить один факториал на другой, и у них сокращаются начальные куски, поэтому мы останавливаемся на n, да, в точности. Ну вот когда берем вот это произведение. Это получается, so this functions when if you now let us ask what is asymptotics with respect to d when d tends to infinity, and this asymptotic n is fixed and this tends to infinity, so it looks like n in the power d divided by d factorial when n is fixed, and t tends to infinity. So this tells you that when t is very large, yes, so we can recover n as the function because we have a very precise collection of functions. And the idea is, so in the polynomial ring, the dimension is precisely the number of variables, and the idea is to keep track on on the value of this function, on value of m modulo mi modulo mi plus 1.
Простите, а точно n фиксированная и d в бесконечности, а не наоборот?
Сейчас. Ну, у нас как бы, мы же
Если у
хотим...
нас n фиксирована и d в бесконечности, то у нас наверху будет не n в d, кажется, асимптотика, потому что d будет очень сильно расти, и много множителей будут прям сильно больше, чем n.
Там многочлен получается.
А, все равно
Там
многочлен
многочлен?
получается.
Да. Там же многочлен, но просто все остальные порядки убиваем.
А, окей, да, экспоненты, видимо, все побеждают.
Да. То есть, ну, как бы у нас растут. Вот, соответственно, ну, как бы идея в том, чтобы вот следить за вот размерностью вот этих величин, да, чтобы установить число переменных, нужно, ну, вот, смотреть за такой размерностью. The problem is when you are speaking about yeah, so also if you can track either about of this, or you can also, so similarly, we can track E mod, so dimension, so you cannot speak about dimension here, yeah, so because with dimension over k.
Да ладно, последний вопрос, там же будет он неправда многочленный, его же степень зависит от этого.
Ну да, например, корень d можно выделить, и там будет оценка какая-то.
Ну, типа там будет слагаемое m d-1 факториал, например.
Да, я наоборот хотел, извините. Ну, вы правы, я хотел все наоборот, да.
Может быть, просто...
Да, не, ну вот тут опечатка, секунду, ну, все наоборот, то есть, извините, так, сейчас. Ну, то есть, тут как бы до внизу n-1 факториал. Оставим. А тут доведем до d. И вот этих элементов получается n-1. Да? И, соответственно, вот это произведение, оно ведет себя как n-1 в степени d делить на n-1 факториал. Да? Вот. И теперь, ну, когда n фиксировано, да, и d стремится бесконечно, то это вот буквально... Спасибо, да, что поправили. Вот, соответственно, ну, как бы, so one can keep track on this kind of value, yeah. So, but one also can track a modulo m square, mi, yeah. But here you have a little bit different situation. So here you have filtration. So I mean, you cannot say that this is a vector space over K, yeah? But you can have the following. So you can associate the so-called length function And naturally, this should be the sum of pieces, sum of dimensions of mi modular mk modular mk minus 1. So where k runs through from 0. Yeah, meaning that you have a modular m, and k is equal to I. So you are keeping track of this kind of dimension, and this can be said as follows. So suppose you have m is some module. Is a module over A, and if you look at so suppose you have you have modulo over A, and M is maximal ideal. So M is called of finite length. Of finite length. If M can be filtrated, like this is filtration, of submodules, those quotients is one-dimensional vector spaces. Or finite dimensional vector spaces. Что? So now you have m0, so 0, m0, m1, etc. So you can write down this filtration where m modular, mi modular, mi minus 1 are finite dimensional vector spaces, finite dimensional vector spaces over A mod M. Yeah, so these are just A modules, and so the claim is that you have such filtration that the structure of A module reduces to the structure of A mod M modules, and these guys are finite dimensional vector spaces. Notice that the length is so we can define the length. So length of M is the maximal length of such chain. So maximal. And this yeah, so this in order to have this notion consistent, yeah, so M should be, M is maximal, should be maximal ideal. And the minimal in the same time, and also minimal. Yeah, so otherwise your module will be of infinite length because of just if m is not не, в смысле тут как бы тут пока тут ничего пока не надо. То есть, как бы, yeah, so, and of course, yeah, so in our, so this length behaves naturally when you have the sequence of modules, yeah, so modules of finite length, so if you have exact sequence of modules.
Сейчас, можно вопрос, а у нас локальная?
А локальная, да, считай, да, исходно. Да, я, наверное, забыл указать, да. Is local. And yeah, so we can speak about this. Yeah, and so actually this yeah, so in a sense this is somehow the general, this is Zhgun theorem, yeah, because if you think this from the viewpoint of representation theory, yeah, so that you have, from the viewpoint of representation theory, you may think the following, so just if you have modules over A, so the module is simple if and only if the quotient is it is a quotient by maximal ideal. Yeah, so that M is simple, M is irreducible, is simple. So doesn't contain proper submodules. If M is isomorphic to A mod M, and where M is maximal. Yeah, so otherwise you can do further homomorphism and this will give you some module of M. So, and actually this associated prime decomposition, it is somehow the way to generalize this decomposition in the simple modules, you know, because you see that A modular prime ideal is not simple. Yes, it's a maximal ideal, a non-trivial maximal ideal in the ring that contains P, so A mod P cannot be maximal, but somehow in associate prime decomposition we're interested in the quotient, most interested in the quotient in the form of A modular. And Jordan-Hölder theorem, Jordan. It says that modules can be filtrated. So if you have a module, that collection of modules where you have where the quotients are simple, So two collections. So two collections of modules. Two filtrations. Such that mi modular mi plus 1 and n I tilde modular mi plus 1 tilde are simple. Then up to permutation that they have the same number of factors. So that then up to permutation. They have the same number of factors. And if you want to generalize the notion of length, yes, so that you see that yes, so you can generalize it like this, yes, and you see that the factors should be simply modules over so that they should be simple modules, and that means that they are isomorphic to a modular maximal ideas. Yeah? So just I mean we assumed that the ring is local, but this is not needed. We simply want to have this to be these factors to be a mod M where M is maximal ideals. And the modules of finite length, so that they behave in a rather special way. Yes, so that you have this kind of thing. So, yeah, so here we have to, now we have to speak, in order to speak about Hilbert polynomial, so the thing is that we want to consider, so game, let me write down game. The following is that calculate, so consider length, so consider dimension of mi modular mi plus 1. So this is a function h of I. Well, let me put them here. So and prove that for large n, and this just this thing will be h of n is a polynomial in n. So what we shall prove actually, we shall prove that this can be written as a rational function. So you yeah, so we shall have some power series. So we shall. Yeah, so how we have to prove it, so in order to, how we can study this, we can study it by, Сейчас, как производящая функция? Generating power source. Generating. Производящая функция, да?
Тоже.
Or this is called Poincare series in this case. And this is nothing as just putting putting additional variable. Putting generated series, so putting these numbers and considering the formal power series. So yeah, so then the question is that by this we can introduce dimension, and in order, I mean, there are two things. First of all, we can prove something about this polynomial. So first of all, prove that it is polynomial. So this will be rational function in our case. Rational function. And this, if yeah, so this is a rational function, and after that we have to compare. So the idea is to consider more general thing, to compare it with. So also the final goal is to calculate this via degrees and relations, and also so we have to compare it with the usual notion of dimension. So with the usual notion of dimension. And how we can compare it with the usual notion of dimension? The idea is that you can do it via the previous statements that we discussed, via the system of parameters. So this can be done. This is done. Via the system of parameters. Because what was the aim? So you had M, and we had chosen the system of parameters. Yeah, so precisely in a way that 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 the number of parameters is precisely codimension of M, which is dimension of the ring, dimension of the local ring, and also the remaining part that if you look at the quotient of A mod x1, xn, it is Artinian ring. And how we may see the condition that our ring is Artinian if you look at this series. На Вартиновом кольце, да, что любой идеал, максимальный идеал, он не потентен, правильно?
Просто это не очень.
Не, да, это ну, буквально, да. Ряд это многочлен, но я хотел просто сказать, что начиная с большого места, да, все просто нулевое. То есть как бы so asymptotically just yes, as it was said that it's just a polynomial. So if the ring is Artinian, this thing is polynomial, and it is if and only if actually. Yeah? So we have proved that if if you have stabilization, so if we have if h of n is 0 for large n, for some n. So this will mean that m is equal to mn plus 1, and this by Nakayama lemma, that this will imply that mn is equal to 0 by Nakayama lemma. And this implies that A is Artinian. So if your you have a local ring where maximal ideal is nilpotent, then A is Artinian. So this is somehow motivation for that, and yeah, so I think just I do not have time to start something. Ну, у нас 5 минут даже всего. То есть, ну, я думаю, что я ничего не успею полезного сказать. Так что давайте. Ну, в следующий раз я расскажу, почему это будет действительно рациональная функция.